followed by, then they use blue, and golly, I don't have a blue pen. So I guess it'd be brown, blue, brown, they both start with B. From B to C, here, was what type of a process was it? That's correct, it was an adiabatic process. So B to C is an adiabat. Oops. B to C, I'm supposed to be using black for the, I don't know if I'm sticking with color code so strictly, but it might be fun. B to C. And then we have an isochoric process, which was done in green from C to D. And that's where we're converting chemical potential energy into thermal energy. Another adiabat, where we're using brown for adiabats. You get from D to E, and from E to B is another isochoric process, and B back to F. Again, an isochoric process. So that was the Otto cycle. A, B, C, D, E, B, F, which is A. Right, it starts over.
Professor?
Yes.
Sorry, can you just go through really quick and say this is like when the piston is going up, this is when
I say what real quick?
Can you just remind, this is when the piston is going up, this is when it's going down, this is when the pressure is at.
Okay. All right, so put in the arrows, which is good. Let me start by simply writing it down. It's going to be A, B, C, D, E, B, F, then A again. So what she's simply asking is a whole lot easier to just draw the arrows on here. So the B to C was an adiabatic compression, C to D, an isochoric increase in pressure, then D to E, adiabatic expansion, E to F, isochoric, I'm sorry, E to B, isochoric again, isochoric drop, and then back again. So there's the system like this. That's the Otto cycle, and we started by defining the efficiency. I'll just write it as the efficiency of the Otto cycle is work out divided by heat in, like this. And that's a pretty logical way to define the efficiency of an engine, because you put a certain amount of energy in and what fraction of that is turned into usable work. Of course, we ignored all sorts of practical things like frictional losses and so on. But we're doing a theoretical calculation here. When we were done, we found that the efficiency of the Otto cycle was 1 minus 1 over R to the gamma minus 1 power, where R was the compression ratio between the largest volume and the smallest volume, represented by the volumes at B and A, or E and D. Anyway, those two volumes there. This is the large volume, this is the small volume here. All right, so we worked that out for two reasons. One, of course, it's a very practical engine. It's very similar to the automobile engine that we use today. And it introduces the idea of talking about efficiencies on a PV diagram. Now, I think it's remarkable that way back in the early 19th century, a young French engineer named Sadi Carnot, who had only one type of engine to think about, was able to derive what we might call the perfect engine, the Carnot engine. And what was that one type of engine that Carnot had to work with in the early 1800s? That's right, only the steam engine, that's all he had. But from that, he was able to idealize a concept which applies to all engines invented since that time and will be invented in the future, all engines. The way it goes is as this. You can imagine this cycle as a very strange looking system. And here's how it's going to work. I'm going to start with a heat reservoir. And I'm going to call that T hot. And sitting on there will be a cylinder made of the perfect thermal insulator. Like that. Fitting in it, and the piston made of the same material, perfect thermal insulator, no gas loss, no friction. Inside there's a trapped ideal gas. And I'm going to start by expanding this system, let's say to here. Now as I pull this thing up to this new position like that, of course, the gas is doing work on the piston. The gas is pushing on the bottom of the piston as the piston moves up. Work is being done by the gas. So energy tries to come out of the gas. I say that because since it's sitting on a reservoir, this is a material like a perfect thermal conductor that is huge, immense. Imagine it to be infinitely large. So that as the heat energy flows into work, more heat energy will replace it. Of course, it's an isothermal process. In other words, I'm saying the change in internal energy of the trapped gas does not change. Hence, therefore, there will be a heat flow to replace the work done. So there is a Q in, and let me just indicate it like that, Q in, and put an arrow like that. That's the only way we can have the expansion. Now we get to that point, and we're going to slide this thing over. Notice that I have drawn over here the perfect thermal insulator. So now I slide the system over to here. And right now it's at this position. Now you'll notice this thing is completely surrounded by perfect thermal insulator. And I'm going to expand it further up to here. In so doing, of course, this is not an isothermal process, is it? In fact, all the work done in moving the piston up, all the work done by the trapped gas comes from the internal energy of the trapped gas. Yes, this is an adiabatic process. So the temperature has dropped, hasn't it? Well, it so happens that right alongside I have another reservoir. Perhaps I'll use green. I don't know what other color to use. I'll put this up. When you use green, I pick up the brown. Oh, I have a very clever idea. I'll use orange because orange is a different color than red. Huh? So now I have a different reservoir over here. At the new temperature, I'm going to call T cold. I'm going to slide the system over to this reservoir. Now let's see, we've expanded to here. This is all perfect insulator. This is a reservoir at the new lower temperature, and I'm going to compress this system back down to some intermediate volume, perhaps about here. So, of course, as I push down on this thing, as the piston goes down, work is being done on the system. The system absorbs that, tries to rise in temperature, but it can't because it's sitting on a cold reservoir. So any energy that I put into the gas in compression will be rejected into the cold reservoir. So here we have Q out. The amount of work done compressing that gas will show up as heat energy rejected to this reservoir. And just like before, the reservoir is considered to be infinitely large, so I don't care how much energy I dump into it, it retains its temperature. So it's an isothermal compression, of course. And now we have had to stop at a very delicately measured position so that I can do one last final compression. I'm going to move this system back over to here now. And perfect thermal insulator here like this goes right here. And I'm going to compress it all the way back to the original position here. On an insulating stand, and so again, we're going to have it be adiabatic. Now I'm going to have to choose that stopping position here very carefully. Let me show you why. I want this system to end up looking like this on my PV diagram. On my PV diagram, I wish to start out at position A up here. And the first thing I did was an isothermal expansion. So I will show that then, this isothermal expansion, down to position B. So we went from position A on this graph to position B. Then we did an adiabatic expansion. The second one was an adiabatic. So that will be done in green, I guess. As you know, adiabats are more extreme than isotherms. We drop to a new lower isotherm at position C. Then we do our first isothermal compression, so there will be another isothermal compression, red for isothermal. And we have to select position D so that it is on a common it is on a common adiabat with position A. So we want to do this process A, B, C, D, A. We want to do this process and make a closed loop. So we have isothermal expansion, isothermal compression, adiabatic expansion, adiabatic compression. We want to start at end at A. We want to make this a closed cycle made of two isotherms and two adiabats. So in a way, the only trick you have to do is very carefully find this position D. Once you determine an isotherm, there is a position D on this isotherm which has an adiabat in common with point A. As we said a moment ago, A to B, heat flows in, Q in, and C to D, we have heat flowing out, Q out. There is no heat flow from B to C or D to A. Even though work is done, there is no heat flow. This is called the Carnot engine. Carnot engine represented on a PV diagram like that. You might be looking at this engine saying, oh, come on, we can't build an engine like that. And you're right. We can't build the engine like that. However, this is the idealized engine that will give you the upper limit of efficiency on any engine. I don't care how you design the engine. Any subsequent engine will be Carnot efficiency or less. It certainly will be less because there'll be friction involved, there'll be losses involved, unaccounted for in the Carnot cycle. So we're going to use the Carnot cycle to represent the idealized engine, the perfect engine. And to do that, let's begin to talk a little bit about the efficiency of a Carnot. Well, the efficiency of a Carnot is defined exactly the same way. Efficiencies are always how much work do you get out divided by how much heat flows in. Well, we know where the heat flow in is, don't we? And we know where the heat flow out is. And I'm about to start by claiming that the Carnot efficiency, I don't think I need these colors now. I'm going to start out by stating that the efficiency in the Carnot engine, just like before, work out divided by heat in. Of course, heat in